Hello and welcome. In this video you will learn how to program this Tetris game in C# using WPF. Let's begin by setting up the project. Go ahead and open Visual Studio. Click the Create a New Project button and then choose WPF as the project template. I will call the project Tetris and leave it in the default folder. Now it will ask about the target framework, and .NET 5.0 is fine. Before we start writing any code, let me show you how we are going to represent the GameGrid. Tetris is played on a grid with 20 rows and 10 columns, but we will add 2 extra rows at the top for spawning blocks. These 2 rows will be hidden, so they won't be visible during gameplay. We will count the rows from top to bottom and the columns from left to right, just like we do for matrices. So, the origin is this top left cell at row 0 and column 0. We will represent the GameGrid using a 2-dimensional integer array. Let's say that this is the current state of the game. In this case, the 2-dimensional array will look like this. Empty cells are represented with the value 0. A cyan tile is represented with the value 1. A blue tile has value 2, an orange tile has value 3, and a yellow tile has value 4, a green tile has value 5, a purple tile has value 6, and finally a red tile has value 7. Note that the current block, the one that can still be controlled by the player, is not reflected in the array. It will be stored separately, as you will see in a minute. Let's return to the editor and write a class to represent the GameGrid. I will create a new class and call it GameGrid. This class will hold a 2-dimensional rectangular array. The first dimension is the row and the second dimension is the column. We will also create properties for the number of rows and columns. And then we will define an indexer to provide easy access to the array. With this in place, we can use indexing directly on a GameGrid object. The constructor will take the number of rows and columns as parameters. This way, the class could also be used in a micro or mega version of Tetris with untraditional grid size. In the body, we save the number of rows and columns and initialize the array. Let's create a few convenience methods. The first one will check if a given row and column is inside the grid or not. To be inside the grid, the row must be greater than or equal to 0 and less than the number of rows. Similarly for the column, but of course it must be less than the number of columns. Next, we will write a method that checks if a given cell is empty or not. It must be inside the grid, and the value at that entry in the array must be 0. We also want a method which checks if an entire row is full. And one which checks if a row is empty. And of course, when there are full rows, they need to be cleared and the rows above should be moved down. Here is how we will clear the full rows. Assume that the GameGrid looks like this, and then I drop an IBlock on the right side. We will use a variable called cleared, which contains the number of rows cleared. Then we start at the bottom row and check if it's full. In this case it isn't, so we simply move on to the next row. This row is full, so we clear it and increment the cleared variable. The third row is not full, but since we have cleared one row below it, it will be moved down by one row. The fourth row is full, so we clear it and increment cleared. Neither of the remaining rows are full, so they will be moved down by 2 rows because cleared equals 2. This process can be stopped when an empty row is encountered, or you can just move down the remaining empty rows. Okay, so let's write a method which clears a row. And one that moves a row down by a certain number of rows. With this in place, we can now implement a clear full rows method. The cleared variable starts at 0 and we move from the bottom row towards the top. We check if the current row is full, and if it is, we clear it and increment cleared. Otherwise, if cleared is greater than 0, then we move the current row down by the number of cleared rows. And in the end, we return the number of cleared rows. Great, now the GameGrid class is done. Let's see how the blocks work and how we can represent them. In Tetris, there are 7 different blocks, each consisting of 4 tiles. Here I have shown the blocks in the state they are in when they are spawned. Each block appears to rotate around a specific point, which we mark with a dot. Most blocks rotate around the center of a tile. For example, the T block rotates around this tile. The I block, however, rotates around this point, which is not the center of a tile. And the O block rotates around this point, so it doesn't appear to rotate at all. There are many ways to represent the blocks, but here is how we will do it. Imagine that there is a bounding box or grid surrounding each block. This grid is just large enough to fit the block in all 4 rotation states. We define the top left cell to be the origin at row 0 and column 0, exactly like we did for the GameGrid. For each of the 4 rotation states, we will simply store the occupied positions in this bounding grid. In state 0, we have tiles at row 1, column 0, row 1, column 1, row 1, column 2, and row 1, column 3. We store the tile positions for the remaining states in the same way. And then we store an integer indicating which rotation state the block is currently in. This way, we just have to change an integer to rotate a block. Alright, we have covered rotation, but the player can also move a block from side to side and down. This can be represented easily by storing a row offset and a column offset. In this example, we have a row offset of 4 and a column offset of 2. To see why that is, we need to consider the bounding grid of the block. Now we can see that the origin of the bounding grid is at row 4 and column 2, and that's why we have that offset. When we want to move a block, all we have to do is change the offset. To represent a position or cell in a grid, we will add a simple position class. This class will store a row and a column. And then we will give it a simple constructor. Next up, we will create a block class. It will be an abstract class, and then we will write a subclass for each specific block. We need the following data for each block. A 2-dimensional position array, which contains the tile positions in the 4 rotation states. A start offset, which decides where the block spawns in the grid. And an integer ID, which we need to distinguish the blocks. Besides that, we will store the current rotation state and the current offset. In the constructor, we set the offset equal to the start offset. Let's write a method which returns the grid positions occupied by the block, factoring in the current rotation and offset. The method loops over the tile positions in the current rotation state and adds the row offset and column offset. The next method rotates the block 90 degrees clockwise. We do that by incrementing the current rotation state, wrapping around to 0 if it's in the final state. Similarly, we will add a method to rotate counterclockwise. Next, we will add a move method, which moves the block by a given number of rows and columns. Finally, let's add a reset method, which resets the rotation and position. The block class is now done. Let's write a subclass for the IBlock. First, let's store the tile positions for the 4 rotation states. And now we will fill out the required properties. The ID should be 1. The start offset should be -13. This will make the block spawn in the middle of the top row. And for the tiles property, we return the tiles array above. That's all we have to do. The functionality is in the base class. I won't fill out the data for all 7 blocks in this video, but let's take a look at the OBlock because it's quite unique. This block is unique because it occupies the same positions in every rotation state. We could copy and paste the same positions 4 times, but that is unnecessary. The code will work just fine if we only provide 1 rotation state. You will write the remaining subclasses yourself. I will show you all the data you need, so just pause the video and fill out the data. As you can see on the right, I have now finished the subclasses for all the blocks. Now we will add a block queue class, which is responsible for picking the next block in the game. It will contain a block array with an instance of the 7 block classes, which we will recycle. We also need a random object. And finally, a property for the next block in the queue. When we write the UI, we will preview this block so the player knows what's coming. You could also store an array here containing the next few blocks and preview all of them. Let's write a method which returns a random block. In the constructor, we initialize the next block with a random block. The last method we need returns the next block and updates the property. Since we don't want to return the same block twice in a row, we keep picking until we get a new one. That's it for the block queue class. Before we start writing the UI, let's create a GameState class which will handle the interactions between the parts we have written so far. First, we add a property with a backing field for the current block. When we update the current block, the reset method is called to set the correct start position and rotation. Next, let's add properties for the GameGrid, the block queue, and a game over boolean. In the constructor, we initialize the GameGrid with 22 rows
and 10 columns. We also initialize the block queue and use it to get a random block for the current block property. Now we will write an important method which checks if the current block is in a legal position or not. The method loops over the tile positions of the current block, and if any of them are outside the grid or overlapping another tile, then we return false. Otherwise, if we get through the entire loop, we return true. You will see why this method is important in a second. Next, we write a method to rotate the current block clockwise, but only if it's possible to do so from where it is. The strategy we use is simply rotating the block, and if it ends up in an illegal position, then we rotate it back. Let's write a method to rotate counterclockwise, which works in the same way. We also need methods for moving the current block left and right. Our strategy will be the same as above. We try to move it, and if it moves to an illegal position, then we move it back. Of course, the block can also be moved down, but we need two other methods before we add that. The first one will check if the game is over. If either of the hidden rows at the top are non-empty, then the game is lost. The next method will be called when the current block cannot be moved down. First, it loops over the tile positions of the current block and sets those positions in the GameGrid equal to the block's ID. Then we clear any potentially full rows and check if the game is over. If it is, we set our game over property to true. If not, we update the current block. Now we can write a move down method. It works just like the other move methods, except that we call the place block method in case the block cannot be moved down. At this point, we have written a lot of code without seeing anything interesting on the screen. So let's import some assets and get started on the UI. We need to create an assets folder. Here are the assets I'm going to use. You can download them by clicking the link in the description below. There's an image for every tile and block in the game, including an empty tile and an empty block. Additionally, there is an icon and a gradient which we will use as the background. You can of course also create your own assets if you want to. Either way, select them and drag and drop them into the assets folder in the project. Select them all, right click, go to properties and make sure the build action is set to resource. Now we are ready to work on the UI. Here we are in the main window.saml file. Let's change the title to Tetris and I will set the default height to 600. I will set the minimum width and height to 600. The background is going to be dark, so let's use a white foreground. I will set the font to Segoe UI Light and the font size to 28. We also need a key down event handler so we can detect when the player presses a key. Let's move down to the grid. For the layout, we need 2 rows. The height of the top row is set to auto and the other row will use the remaining height. Then we need 3 columns. For the middle column, we set the width to auto, and the remaining width is shared between the other two columns. Let's use the gradient in the assets folder as the background. The GameGrid will be drawn on a canvas control in row 1 and column 1. We make the background a dark gray color and set the width to 250 and height to 500. That's 25 pixels per visible cell in the GameGrid. If we run the program, it looks fine, but there is a problem. The canvas doesn't scale with the window size. To fix that, we wrap the canvas in a view box. We just have to specify the grid row and column on the view box instead of the canvas. And let's add a small margin to the bottom as well. Now the canvas scales with the size of the window while still preserving the correct aspect ratio. On the canvas, we will set clip to bounce to true and add a loaded event handler. Clip to bounce ensures that any children that extends outside the bounds of the canvas will not be shown, and we need this for our hidden rows. Above the GameGrid, we will display the score. So let's add a text block in row 0 and column 1. In row 1, column 0, we will show what block is currently on hold. We add a stack panel containing a text block with the text hold and an image control for the image of the held block. On the right side of the canvas, we will show the player what the next block will be. Again, we use a stack panel with a text block and an image. The final thing we need is a simple game over menu. It will show the player's final score and contain a button for restarting the game. We use another grid with a semi-transparent background and make it span both rows and all 3 columns. Inside the grid, we add a stack panel, and inside that there will be a text block with the text "Game Over." Below that, we will show the player's final score. And finally, a green Play Again button with a click event handler. Initially, this menu should be hidden, so we have to set visibility to hidden on the grid. That's it for the UI. Let's bring it to life. I have navigated to this file, which is known as the code behind. In this video, I will not use the MVVM pattern. We will just keep it simple and control the UI from here. First, let's set up an array containing the tile images. The order here is not random. At entry 0, we have the empty tile. The order of the remaining tiles matches the block IDs. For example, the IBlock has ID 1 and should be cyan. Therefore, we have the cyan tile at index 1. Similarly, the OBlock has ID 4 and it's yellow. Therefore, we have the yellow tile at index 4. We need a similar array for the block images, which will be used to show the held block and the next block. Again, the order matches the IDs. Next, we will declare a 2-dimensional array of image controls. The idea is that there is one image control for every cell in the GameGrid. We will set this up in a second. And then of course we need a GameState object. Let's create a method to set up the image controls correctly in the canvas. The image controls array will have 22 rows and 10 columns, just like the GameGrid. Next, we create a variable for the width and height of each cell. Recall that we set the canvas width to 250 and the canvas height to 500. This gives us 25 pixels for each visible cell. Now we loop through every row and column in the GameGrid. For each position, we create a new image control with 25 pixels width and height. And then we have to position this image control correctly. Recall that we count rows from top to bottom and columns from left to right. So we set the distance from the top of the canvas to the top of the image equal to r-2 times cell size. The -2 is to push the top hidden rows up so they are not inside the canvas. Similarly, the distance from the left side of the canvas to the left side of the image should be c times cell size. Next, we make the image a child of the canvas and add it to our array, which will be returned outside the loop. Just to be clear, we now have a two-dimensional array with one image for every cell in the GameGrid. The two top rows, which we use for spawning, are placed above the canvas, so they are hidden. Alright, in the constructor, we can initialize the image controls array by calling this method. Now it's super easy to draw the GameGrid. We loop through all positions. For each position, we get the stored ID and set the source of the image at this position using the ID. Drawing the current block is also easy. All we have to do is loop through the tile positions and update the image sources in the same way we just did. Let's add a draw method which draws both the grid and the current block. We will call the draw method when the game canvas has loaded. If we start the program, we can see an empty grid. The current block is also there, but it's above the canvas, so we cannot see it. Let's detect some key presses. First of all, if the game has ended, then pressing a key should not do anything. We will use the arrow keys for movement. The up arrow will rotate the block clockwise, and the set button will rotate counterclockwise. We will also add a default case where we simply return. And outside the switch, we call our draw method. The default case ensures that we only redraw if the player pressed a key that actually does something. Here is the game so far. The block can be moved down and from side to side. We can also rotate it both clockwise and counterclockwise. If we move a block all the way down, it is placed in the grid and we get a new one. We can also clear rows, but Tetris would be pretty easy if the block didn't move down by itself. So let's add a game loop method. It has to be async because we want to wait without blocking the UI. First, we draw the game state. Then we add a loop which runs until the game is over. In the body, we wait for 500 milliseconds, move the block down and redraw. We start the game loop when the canvas has loaded. Now this is starting to look more like Tetris. The next thing we will do is handle game over. Up here in the game loop, we know that the game is over when we exit the loop, so we just have to make the game over menu visible. When the game is lost, we see the game over menu, but this button doesn't work yet, so let's fix that. The play again click method is called when the player presses the play again button. Here we will create a fresh game state, hide the game over menu, and restart the game loop. Now we can restart the game. The next thing I want to fix is the spawn position. Our blocks spawn in the 2 hidden rows, but if there is space in row 2 and 3, the top visible rows, it would look better if they spawned there. So let's head over to the GameState class. In the setter for the current block, just below the reset call, we will move the block down by 2 rows if nothing is in the way. Now the blocks spawn nicely. Another thing is, when you lose the game, you cannot really see which block killed you. We can fix that by showing a few pixels of row number 1, which is currently hidden. Let's open up the UI and change the height of the canvas to 510. And then we go to the code behind and scroll up to the setup game canvas method. When we position the images vertically, we will add 10 pixels. Now we can see just a little bit of row number 1, which is nice when we lose the game. Let's preview the next block. Now we can always see which block will come next. Next, we will add a score. So let's add a property to the GameState class. In this project, the score will just be the total number of rows cleared. So we have to head down to the placeBlock method. Recall that clear full rows returns the number of cleared rows. So we can just increment the score by that amount. Let's go back to the code behind and set the score text in the draw method. We also have to set the final score in the game over menu. Now we have a working score. And if we lose the game, we also see the final score here. In most Tetris games I have played, there's also an option to hold a block. Let's go back to the GameState class and add a property for the held block and a canHold boolean. In the constructor, we set canHold to true. And then we create a hold block method. If we cannot hold, then we just return. If there is no block on hold, we set the held block equal to the current block and the current block equal to the next block. If there is a block on hold, we have to swap the current block and the held block. In the end, we set canHold to false, so we cannot just spam hold. The last thing we have to do is scroll down to the placeBlock method and add canHold equals true under the line where we update the current block. Then we go back to the code behind and call hold block when the player presses C. And then we create a method which shows the held block, and we will call it from draw. Now we can hold a block, and we can see which one is on hold on the left side. The next thing we will add is a hard drop feature. It enables the player to press one button, which will move the block down, not just by one row, but by as many as possible. We go back to the GameState class, and here we will write a little helper method. It takes a position and returns the number of empty cells immediately below it. With this method, we can find out how many rows the current block can be moved down. We invoke it for every tile in the current block and take the minimum. And then we create a drop block method. It moves the current block down as many rows as possible and then places it in the grid. Back to the code behind. We will call drop block when the spacebar is pressed. That's great, but it's even more useful if you can see where the block will land. So let's add a so-called ghost block. The cells where the block will land are found by adding the drop distance to the tile positions of the current block. Then we set the opacity of the corresponding image controls to 0.25 and update the source. Setting the opacity is a nice trick. We just have to remember to reset it when we draw the grid and the current block. Draw ghost block will be called from the draw method, and it has to be called before draw block. Now it's super easy to see where the block will land. There is one final feature we will add to this game. The current block should move down faster and faster as the player increases their score. Let's add a few constants to control the delay between moving the block down. I use 1000, 75 and 25, but feel free to play around with these values. In the game loop, we add a delay variable. When the game starts, the delay will be max delay. For each point the player gets, the delay is decreased by delay decrease, but it can never go below min delay. In the beginning, the block moves down very slowly, but after increasing the score, the block moves much faster. The game is done, but let's add an icon. Open the Solution Explorer, right-click on the project, click Properties, and go down to the icon and type in assets/icon.ico. You have now programmed a Tetris game in C# with a lot of cool features. I really hope you enjoyed this video and that you learned something. Please consider leaving a like and subscribing to my channel. Thank you so much for watching.